Dear students, let's talk about ANOVA, which is analysis of variance. So let's say if you are comparing two samples, example could be, let's say you are comparing two different batteries. Let's say AGS battery and second one could be Osaka battery, and you would like to know that which battery is giving me more, or which battery has got more life on average. So what you can do, you can take few samples, let's say maybe 10 or 20 batteries from AGS, and find for how many months or for how many time each battery worked. The same procedure you will do for Osaka battery. Okay, and next step would be to find whether there is a difference between the mean life or average life of those brands of batteries. So you will apply t-test for this one, right? Or if your sample size is high, you can always use z-test to compare two means. So here we were saying that we had two different samples and we were comparing it. Okay, next step would be a little advanced. Let's say if I am running an experiment at different levels, so then it is not advisable to use t-test or z-test, because for every level I will be performing t-test and z-test, and there will be so many z-tests and t-tests. For this purpose, a very easy method is deployed, and it is called ANOVA, analysis of variance. Analysis of variance was developed in the early 1920s by Fisher and was applied to agricultural experiments. A very simple examples would be, let's say I would like to study the effects of 5 different brands of gasoline on automobile engine efficiency, right? So very easy uh, methodology would be to use the single factor ANOVA or one way ANOVA. Here summary of whatever I said, that let's say I have a sample and I want to compare it with a number mu naught, right? Let's say if my battery mean value is 25 or 30, 30 could be months, right? So I will be using univariate t-test. If I am comparing two sample, univariate t-test will be used when I am comparing two samples. One sample would be AGS battery, and I have, let's say, 20 observations, and sample 2 or sample Y would be Osaka battery, and then I can compare that, okay, using two sample univariate t-test, that whether they have differences in their mean values or not. And if I have many um, samples, let's say 20 or 30 samples here, then using t-test is not feasible, because I will be performing so many t-tests here. So as I mentioned before, that it is advisable to use ANOVA in such situations. um, ANOVA calculations are usually done via computers and some popular software packages such as Minitab, Excel, SPSS. They will give you directly p-values, and on the basis of p-value or f-value, f naught, you can make decisions regarding hypothesis or null hypothesis. In analysis of variance, the null hypothesis is that all means are equal, and alternative hypothesis is that at least one pair is not equal. Small n would be number of replicates, and small a would be treatments or levels of the factor, um, while capital N, which is the total number of replicates or total runs, that would be a multiplied by small n. So here is your null hypothesis, and if at least two of the means are not equal for those levels, then we will reject the null hypothesis. And it should be noted that rejecting the null hypothesis does not require that all means are significantly different from each other. If at least two of the means are different, then the null hypothesis will be rejected. So let's say if I am running experiment at 15%, 20%, 25%, 30, 35%, so it will be comparing all those means, and if there is a statistical significant difference between any two levels, right, the null hypothesis will be rejected. Here you can see that the decision to whether reject null hypothesis or fail to reject null hypothesis is made on the basis of f value or p value. So here f naught here is basically ms treatments divided by mse, which is basically the variation in variation between treatments. So let's say I have 4 or 5 levels or treatments. What is the variation between treatments divided by variation within group or within a treatment. So if null hypothesis is false, then the f statistic value will be large, and large f value means that this ms treatments is large. This means that the variation between treatments is large. So I will show it graphically here with the help of this figure. So if within, so here is a scenario, we have small f statistics, and here this thing here, this is within group, and how far this is for group, this is the mean for group 1, this black line is mean for group 2, this is mean for group 3, and this is my grand mean. And this blue, right, this is basically variation within group, and how far are they from one another, this is variation among group. Here in the second, here within variation is small, here within group variation is more. You see, here within group variation is small, so they are not touching this grand mean. So when within group variation is small, the f test statistic value will be high, because here it's in the here. If this is small, this thing will be high, and we will reject null hypothesis because the f statistic value is very high, and it is very high compared to our f threshold value, which we will which we can look up in f table. And this at f cutoff would be f alpha comma a minus 1, where a are my levels, into comma a multiplied by n minus 1, where n is my number of runs for each experiments. Here is the standard ANOVA table between treatments. Source would be SS treatments, within variation would be SSE, and then total variation would be the summation of SS treatments plus SSE. That will give me total variation. If I am dividing it with the corresponding degrees of freedom, it will give me mean square treatment and mean square error here, and f statistic will be ms treatments divided by mse. And if this f naught value is greater than the threshold value, we will be saying okay, we reject null hypothesis. If this f test statistic value is small, we can say we fail to reject null hypothesis. So let's consider a very simple example. Here we are interested in this particular example, we are interested in finding that which particular percentage of cotton will give me maximum strength, maximum tensile strength. So I have here different percentage of cotton: 15%, 20, 25, 30, 35. So here my A is 5, because 1, 2, 3, 4, 5 here. My small n here is also 5, because I am taking 5 observations for each level or each treatment. And my total number of runs are n multiplied by n, so 5 into 5, 25. So I have like total 25 number of experiments. So after using let's say Minitab, it is giving me f naught, which is 14.76, and the cutoff value is, we can look it up in table. They are taking this alpha as 5%, and for 4 comma 20, which is basically a minus 1 and then a multiplied by n minus 1. So 4 comma 4 multiplied by 5, and this value is 2.87. This means that the cutoff value is here, 2.87, somewhere over here. However, my test statistic value is 14, so it's very far from my cutoff region. So from this we can say, okay, we are rejecting null hypothesis, means that our initial hypothesis was that the strengths or the mean values of strengths are equal. However, we are rejecting it. This means that the treatment means differ. Here is that value of the cutoff value of f. So from this conclusion is very clear that at least one of the treatment means are different. So this means that if you are changing cotton percentage, it is also changing the strength or the tensile strength of the fiber. Means cotton weight percentage will affect the tensile strength of the fiber. And if I'm going to draw this confidence interval, I can see that this one, I think, which was how much was it, 15%? Okay, the first one was 15%. This is for 20%, 25%, 35, 30%, and 35. So here you can see here the confidence intervals are not overlapping with this one or even this one. So from this we can say that, okay, graphically we can see that there is a statistical difference between two means, and the cotton fiber percentage is actually affecting the tensile strength, or it has this effect. Another would be this 30% is very far from 35 also, and from this graph we can see that, okay, this 30% is giving me a very good strength, right? However, if I'm saying, okay, 25 versus 30, so for this particular two, I cannot say that there is a statistical significant difference, because you see they are overlapping. If they are overlapping, then you can say, okay, that there is no statistical significance difference between the means value. But here if you see 15 and 30, so huge difference, 30 and 35. So the conclusion would be that we are basically rejecting null hypothesis. Here is another way of representing confidence interval. Here you can also make decision on the basis of p-value. So my p-value is very small. If my p-value is smaller than alpha, which is 5%, then I will reject null hypothesis. Let's say this is my data for tensile strength example, right? You could do this analysis in Minitab and Excel. So in Excel you can do it two ways. One would be to do it manually. Second would be to use this data analysis tab. However, if you want to do this analysis in Minitab, first you have to transform your data from rows to columns, because Minitab is operating in columns. So X, which is my treatment for 15th, my first value is 7, 7, then 15, then 11, then 9, and then for the second X, my second level, which is 20% cotton, so it's my values here 12, 17, 12. And next step would be to copy paste this in Minitab. After copy pasting in Minitab, what I need to do is to go to Stat, Innova, click on One Way Innova, right? Then C1 is my response, C2 is my factor, or C2 is my levels or treatments, you can say. After that, all I need to do is to hit OK, and this will give me the values here. I can make decision on the basis of F statistic, but for that I need to know the cutoff value using F table. If I want an easier method, that would be making decision on the value on p value here. So this is your Innova, One Way Innova lecture. Thank you, take care.